Hey everyone, and welcome to this explainer. Today, we're diving into a really critical battleground when it comes to hybrid dual-motor PCS systems. Specifically, we're targeting a high-stakes threat known as fault B10, that's cooling insufficiency and thermal resistance rise right inside an EV inverter. We're going to break down the exact physical mechanisms that cause these power modules to fail, and more importantly, how cutting-edge ASIL D level engineering stops a catastrophic loss of propulsion literally before the driver even knows there's a problem. So we're not just looking at what breaks, we're tearing down the exact hardware, software, and manufacturing defenses that keep these massive power electronics alive under some seriously extreme stress.
To put this into perspective, picture this. You're driving down the highway, full speed. Deep inside your EV's inverter, a cooling channel suddenly gets blocked. Almost instantly, the temperature of those silicon carbide chips starts skyrocketing. The system has exactly 60 milliseconds to react. That's it. It has to detect the spike, diagnose the root cause, and execute a complex safety maneuver to stop the hardware from, well, literally melting down and causing a complete loss of vehicle control. 60 milliseconds. That is the extremely tight fault-tolerant time interval we're dealing with when fighting a thermal resistance rise.
Okay, so here is our blueprint for tackling this thermal threat today. First, deadly heat and root causes. Second, software and hardware code diagnostics. Third, genetic modification via DFMEA design. Fourth, strict gatekeeping in the PFMEA process. And finally, extreme tests during DVP&R validation.
Let's jump into Section 1, Deadly Heat and Root Causes.
To defeat any enemy, you first have to understand exactly how it attacks, right? And in the world of high-power EV inverters, the enemy is thermodynamics. Extreme temperature swings act as this lethal, invisible adversary trying to tear the hardware apart. At a microscopic level, this triggers something called the pumped-out effect. Basically, between the base plate of the power module and the aluminum heatsink, there's a thermal interface material, or TIM. Now, in an automotive environment, this whole setup undergoes wild temperature swings. We're talking -40 to +150 degrees Celsius. So think of it like constantly squeezing and releasing a tube of toothpaste. The thermal expansion and contraction literally pumps that paste out over time, leaving behind these tiny, microscopic air gaps. And since air is a terrible conductor of heat, the thermal resistance shoots through the roof, and the heat simply can't escape into the coolants anymore.
But while the pump-out effect attacks that thermal interface, heat actually finds three other primary ways to destroy the system. First off, you've got fatigue and voiding in the die-attach layer. Because different materials expand at different rates, constantly cycling the power creates these microcracks right under the chips, forming deadly hotspots. Next, you have coolant channel blockages. If the water pump degrades or if scaling builds up on the aluminum walls, your convective cooling just vanishes instantly. And finally, busbar preload loss. If a bolt vibrates loose, the electrical contact resistance at that joint spikes. Pushing massive currents through a loose connection causes violent local joule heating. It basically turns that loose connection into a glowing heater element, pumping heat straight into the bottom of the power module.
Moving on to Section 2, Software and Hardware Co-Diagnostics.
So how exactly does an ASIL D-rated inverter defend itself against all these physical attacks? Well, there's this really fascinating contrast between the hardware and the software. On the hardware side, you've got NTC thermistors embedded directly on the board, converting temperature to a voltage. The hardware acts as this microsecond reflex, so if the voltage drops below 0.5 volts or spikes above 4.5 volts, a hardware comparator instantly flags a broken wire or a short circuit. But here's the catch. Those physical sensors actually have a 50 to 200 millisecond lag, and frankly, that's just way too slow for a chip that's actively melting. So to compensate, the software brain runs a dynamic Foster RC thermal network. It's essentially a digital twin of the inverter running in real time. By crunching the phase current, voltage, and switching frequency, the software mathematically predicts the junction temperature before the physical sensor even feels the heat.
Now, if that predictive software brain detects that the thermal resistance has jumped by, say, 20% over its factory baseline, or if the temperature hits a critical 175 degrees Celsius, it triggers the ultimate safety fallback, and it does it within that strict 60 millisecond window. But what's super clever is that the system bifurcates its defense depending on how fast the car is moving. At lower speeds, under 20 kilometers per hour, it just opens the circuits and lets the motor freewheel, completely safe. But at high speeds, over 80 kilometers per hour, freewheeling could actually cause a massive, dangerous overvoltage. So instead, it triggers a stepwise active short circuit. And to make sure that short circuit doesn't just burn out one single set of switches, the software alternates the short between the upper and lower bridge arms. This brilliantly spreads the heat out evenly, keeping the inverter alive just that much longer.
All right, on to Section 3, Genetic Modification via DFMEA Design.
We've seen how the system reacts during a crisis, but obviously the absolute best defense is preventing the crisis in the first place, right? And that brings us to the drawing board phase, the DFMEA, or Design Failure Mode and Effects Analysis. This is where engineers essentially modify the very DNA of the inverter so it natively survives all this extreme thermal abuse. So the crucial point here is this massive number, 960 degrees Celsius. In older designs, power chips were attached using standard solder. The problem? Solder degrades fast under intense thermal cycling. To bulletproof these new generation inverters, engineers mandate nanosilver sintering for the die attach layer. Nanosilver has a staggering melting point of 960 degrees, and it offers 3 to 5 times the thermal conductivity of traditional solder. It's an absolute game changer. It literally multiplies the power cycling lifespan of the hardware because it ensures the chips never delaminate from their base.
And hey, the physical design upgrades definitely don't stop at the chips. The heat sinks themselves go through an intense 3D thermal co-design process. By integrating pin fins or microchannels directly into the cooling flow, they managed to drop the thermal resistance from the case down to the heatsink to below a staggeringly low 0.1 Kelvin per watt. Meanwhile, over on the electrical side, the bill of materials strictly locks in Class 1 C0G ceramic capacitors. These are amazing because they maintain their exact value regardless of the temperature, and they pair them with ultra-precise thin film resistors. This whole setup guarantees that even when the inverter is just baking in high temperatures and rattling with violent vibrations, the analog signal processing won't drift at all. The foundation is mathematically rock solid.
Let's look at Section 4, Strict Gatekeeping and the PFMEA Process.
Okay, but designing a perfect system on a computer means absolutely nothing if you can't build it flawlessly on the line every single time. This is where process failure mode and effects analysis steps in. We're talking about a series of ultra-strict prevention processes on the factory floor that stop defects dead in their tracks. Remember that amazing nanosilver sintering layer we just talked about? Well, it's only amazing if there is 0 air bubbles trapped inside it. So on the production line, every single module has to pass through a 100% inline 3D X-ray or an ultrasonic scanning microscope. The hard and fast rule? The total voiding rate must be less than or equal to 5%, and no single void can be larger than 1%. If a module fails this check, the production line automatically locks down and isolates that part. It stops a future hotspot before it even makes it into a car.
And that exact same zero-tolerance policy applies directly to the thermal interface material, too. Manual scraping or hand application, completely banned. The factory floor uses fully automated, high-precision stencil printing. And literally immediately after printing, a 3D laser system scans 100% of the surface to verify the thickness is exactly 50 micrometers, with a microscopic tolerance of just 10 micrometers. This automated laser check guarantees perfect uniformity, meaning absolutely no trapped air bubbles.
The final process gates are honestly just as intense. To make sure coolant never leaks and causes a catastrophic short circuit, the fully assembled heat sinks go through a dual-stage helium leak test, pressurized to 4 bar. Finally, to prevent those bus bars from vibrating loose and sparking that localized joule heating we talked about, the assembly uses torque angle servo fastening. But guys, this isn't just a smart wrench. Optical character recognition cameras actually verify that the bolts have a specific phosphate coating on them to ensure the exact right amount of friction. If the servo detects even a tiny deviation in the clamping force, the whole line stops. The end result is a contact resistance permanently clamped to less than 5 microohms.
And finally, Section 5, Extreme Tests during DVP&R Validation.
All right, so we've engineered the perfect DNA and we've built it flawlessly on the factory floor. The very last stage is validation. You can basically treat this as a brutal, unforgiving boot camp. These components are put through simulated lifetimes of absolute abuse. If they can't survive this, there is no way they're ever allowed on the road. Just looking at the passing metrics shows you how violent this boot camp really is. First, the modules get blasted with over 100,000 active power cycles, intentionally violently fluctuating the junction temperature by 80 Kelvin. To pass, the thermal resistance cannot degrade by more than 10%. Next, they throw the inverter onto a vibration table while simultaneously hitting it with rapid cold shocks, from -40 all the way to positive 125 degrees Celsius, while blasting 4 bar of coolant through the channels. The acceptance metric? 0 fatigue cracking. None. Finally, the ultimate test of the software brain, hardware-in-the-loop fault injection. While running a simulated motor at a screaming 12,000 RPM, they instantly block the coolant flow. The system has to prove it can execute that fault diagnosis in under 60 milliseconds, trigger the active short circuit, and successfully clamp the DC voltage to under 720 volts, all without a single component burning out.
Defeating this invisible thermal enemy takes incredibly tight synergy. You need physical metallurgy, precision manufacturing, and just brilliant predictive software all working together perfectly.
The stakes here are an ASIL D safety rating, which means there is absolutely zero margin for error. Which really brings us to a final critical question for you to think about. To accurately predict these sudden thermal spikes and deploy active derating correctly, you need absolutely flawless data. So is your engineering team actually ready to build the dynamic 4-stage Foster RC thermal simulation model required to survive these kinds of extremes? It's a massive challenge for sure, but as we've seen today, with the right architecture and the right processes, it's one we can absolutely conquer. Thanks so much for joining me on this deep dive into EV inverter thermal management, and I'll catch you in the next explainer.